All right, let's jump right into this explainer. Today we're starting a bit of a builder's journey, looking at exactly how invisible magnetic forces are wrangled to construct the electric motors that pretty much run our modern world. From the tiniest vibration motors hidden inside our smartphones to massive industrial engines, the foundational physics are exactly the same, and that is precisely what we're going to unpack today.
Here is our roadmap for today. 1. Magnetic force and conductors. 2. From force to torque. 3. The math behind the spin. 4. Building the DC motor. 5. Real-world applications. And 6. Master the exam.
So let's start with Section 1, Magnetic Force and Conductors.
If we're going to build anything that actually spins, we've got to start with our raw materials, the magnetic field and electrical current. Now, a magnetic field is simply a space where a magnetic force can be felt. But the absolute magic happens when you drop a live conductor right into that space. It doesn't just sit there passively. It actually experiences a physical push or pull. And, we absolutely have to understand that basic fundamental interaction before we can even think about building a working motor.
So, let's break down exactly how we calculate that force on a wire. It all comes down to a neat little formula. F equals BIL sine theta. The force F depends on three main things. First, B, the strength of the magnetic field. Then I, the amount of current flowing through. And L, the actual length of the wire that's inside that field. But then geometry crashes the party. We have to factor in the angle, theta, which is simply the angle between our wire and those magnetic field lines. Smash those all together, and you've got your master equation for the force on a single straight wire.
Which brings us to Section 2, from force to torque.
Now, let's see what happens when we take that straight wire and bend it into a rectangular coil. To understand this, we first need to define torque, which is simply the turning effect of a force. You calculate it by multiplying the force by the perpendicular distance from the axis of rotation. So tau equals F times d. Think about trying to push open a really heavy, solid wooden door. If you push right at the hinges, you get zero turning effect, right? But if you push at the handle, the absolute furthest point from the hinge, you get the maximum effect. That is torque in a nutshell.
Okay, now picture our flat, rectangular wire coil sitting right between the north and south poles of a magnet. Because the current travels up one side of the loop and down the other side, it's flowing in entirely opposite directions. That means the opposite sides of the coil are going to feel equal but entirely opposite forces. One side gets violently shoved upward and the other side gets yanked downward. Because these opposing forces are perfectly balanced across an axis, they create what physicists call a couple. And it's exactly this pair of forces working together that makes the whole coil spin.
Moving right along to Section 3, the math behind the spin.
Let's take that math from our single wire and scale it all the way up to a spinning coil. We just assemble the pieces step by step. Start with our original force equation, F equals BIL sine theta. Then, just like with our heavy door analogy, multiply that force by the perpendicular distance across the coil to get the torque. Finally, expand that out for a full coil, which probably has multiple wraps of wire, not just one. That gets us to our final master equation, tau equals NBIA sine theta.
What's super cool about this equation is how it perfectly highlights the extremes. Because we're using sine theta, the angle completely dictates the sheer power of the spin. You're going to get the absolute maximum turning effect, tau max equals NBIA, when theta is exactly 90 degrees. On the flip side, you get literally zero torque when theta is 0 degrees. The sine of 0 is 0, so in that specific position, your coil just doesn't want to turn at all.
Think of these variables as literal dials you can turn to boost your motor's torque. Want more power? You can crank up N, the total number of wire turns. You can dial up B, the magnetic field strength measured in Teslas, or increase I, the electrical current in amperes. You could even bump up A, the physical surface area of the coil. Once you know these inputs, you literally know exactly how to engineer a much stronger motor.
Next up, Section 4, Building the DC motor.
All right, time to assemble this machine, using everything we just learned. But before we flip the switch, we kind of need to know which way this thing is going to spin. I actually want you to hold up your left hand for a second. Point your index finger in the direction of the magnetic field, and your middle finger in the direction of the electrical current. If you do that, your thumb will automatically point in the direction of the force. It seriously feels like a magic trick, but Fleming's left-hand rule is the absolute best tool for predicting how a motor will move. So we turn it on and our coil starts to spin. Awesome, right? Well, actually, we hit a massive problem almost immediately. Once the coil flips exactly halfway, the relative forces reverse. Instead of spinning, the coil would just helplessly bounce back and forth. But here is the genius fix, the split-ring commutator. It's this clever mechanical switch that physically breaks the circuit right at the half turn, reversing the current direction. By flipping the current every single half rotation, those forces stay perfectly aligned and the coil just keeps spinning continuously in one smooth direction. It's pure genius.
Let's shift gears to Section 5, Real-World Applications. So how does all this translate to the stuff you use every single day? Well, electric motors are the obvious one, driving everything from desktop fans to massive factory conveyor belts. But it's not just about raw mechanical power. This exact turning effect is actually the beating heart of super precise measuring tools in the physics lab. Moving coil galvanometers, ammeters, voltmeters, they all use a tiny, delicate coil floating in a magnetic field. When current flows, the precise torque generated turns a needle on a dial, giving us an exact measurement.
And finally, Section 6, Master the Exam.
Okay, let's pivot from building motors to making sure you can actually crush your exams without falling into the painfully common traps they set for you. Let's test this right now. If a coil's plane is perfectly parallel to the magnetic field, what is the angle theta in our equation? This is literally the #1 trap in conceptual questions. Your brain sees the word parallel and immediately screams, "Ah, parallel, that's 0 degrees." But hold on a second.
Here is the trick. Theta is the angle between the field and the normal to the plane of the coil. The normal is just an imaginary line poking straight up, completely perpendicular to the surface. So if the plane itself is perfectly parallel to the field, its normal is actually sticking out at exactly 90 degrees. Remembering that tiny distinction will absolutely save your grade. Other classic mistakes? Confusing a linear force with rotational torque, doing the math perfectly but forgetting to multiply by n for the total number of turns. And, honestly my favorite, sitting in the exam room trying to use your right hand for Fleming's left-hand rule. Seriously, don't be that student.
To wrap up this explainer, I really want to leave you with this thought. We've talked about the basic equations of torque and magnetism today on a pretty conceptual level. But how do these exact same principles scale up to power the electric vehicles that are completely revolutionizing our highways right now? The jump from a simple textbook diagram to a high-performance EV engine is really just a matter of scaling the exact variables we talked about today. More turns, more current, and massive magnetic fields. So the next time you see an EV silently zip past you, I want you to picture the intense magnetic fields and those perfectly timed commutators furiously spinning away inside. Keep questioning how the physics of your world works, and thanks for hanging out with me today.